Okay, what we're going to talk about today in section 6.2 is the natural base E. This is still exponential form. Mouse. There's still growth and there's still decay. Remember, growth goes away. Whoa, that's a fat marker. I don't want that one. Let's make it thinner. Growth goes away from x-axis. And remember, decay goes towards x-axis. So what happens? Growth gets bigger, the y values get bigger, and decay, the y values get smaller. So that's why it goes towards. So what we have here is, instead of having a number in parentheses, we have this E. In E is what the natural base is. Okay. There should be a K here, and it should also be here. I'm not sure why I didn't include it in the notes. A is still your y-intercept, where it begins. K is your percent increase. And so you don't have to do anything with 1. It's just the percent increase. Over here, A is still your y-intercept. And K for this one, because it's a negative, it's your percent decrease. It's how much it went down. Okay, so what we're going to do is we're going to skip some of this stuff, and then we're going to go down and look at some problems. So we're going to look at numbers 1 through 4. We're going to determine if it's growth or decay. And again, growth is going to be a positive exponent. Decay is going to be a negative exponent. So here's this one. That is a positive exponent, so it's growth. And then it's 1.3. Well, 1.3, if I move my decimal 2 places, is 130% growth. This 2 would mean that I start with $2, or I start with 2 Pokemon cards, whatever it is that you start with 2 there. All right, so now we look at the next one. That is a positive number, so it's growth. And so this is growth. And it's 3, and so if I move the decimal place 2 places, it's 300% growth. We're going to go back and graph it at the end. Right now, we're just going to kind of talk about the growth decay. Okay, so this one, number 2, I kind of went out of order. Again, this is another positive one. So it's growth again. And it's 0.97, so I move it 2 places, so it's 97% growth. And then lastly, number 4. It's positive again, even though it's a small number. I don't know why I have all growths. Well, I'll make up a decay one in a second. So growth, and it's 0.023, so I move it 1, 2, so it's 2.3% growth. Not quite sure why I didn't have any decay ones, but here, let's look at some decay ones. So y is equal to, let's say 2,000. You start with $2,000, and you're spending it exponentially. So we'll do negative 0.2x. And so because this is a negative decimal, or a negative number, that tells us that it is decay. And 0.2 as a decimal, I move over 2 places, so it's 20% decay. Now, one thing I did not talk about with the base E means it's continuous, so it means it just continuously over and over and over and over. It's happening, it's calculated. Okay, so let's look at the graphs of these. We're essentially just, for this one, it crosses at 2, and it's growth, so it goes away. Okay, for number 2, it crosses at 3, and it's growth, so it goes away. Okay, 3 and 4, the same idea. But let's look and see what happens for 5, because 5 is a decay one. It looks a little different. So it crosses at 2,000. No way I'm making 2,000 tick marks, so I'm just going to say that this is 2,000. And decay goes towards the axis, so it's going to go towards the axis. Okay. All right, so now let's look up at some other types of problems. The real reason that we're going to have continuous growth and decay is for compounding and compounding continuously. And what happens is it's paid T times per year. Where'd my thing go? So compound interest is paid continuously, infinite times per year. Infinite, I don't know why I said T. So P is your principal. What do you start with? R is the rate. You need to write it as a percent. And T is time, how many years. Okay, so let's look at this. You are given $2,000 from your last dividend to put in savings. You're going to earn a continuous rate of 4% for 20 years. So when I plug this in, I start with 1,200. It's going to be continuous. Whenever you see this word continuous, you have to use E. 4% as a decimal is 0.04, and I'm going to times that by the number of years, 20. Okay, so if you have a graphing calculator, this is how you're going to type it in. You're going to type in 1,200 times, now right here, let me see if I can draw on this. Oops, I lost the thing. Right here, there's an E to the X, and you see how it's blue. So I have to hit second, E to the X, and then I'm going to do 0.04 times 20, and it keeps it as the exponent. So after 20 years, my $1,200 has now grown to $2,600. Oh, I lost it. $70.65. Now, I know a lot of you do not have graphing calculators, so I'm going to show you another way that you could do it. Okay, so I just did a Google search online calculator. Here's the basic one, but I need the scientific one, so you can actually, if you have a scientific calculator, so I scroll here, here's scientific calculator. Okay, so I had to try it out to make sure I knew how to get it to work because it wasn't working at first. How do I clear this thing? Okay, clear, there we go. So when you're doing E, it doesn't really read it in order. So what I'm going to do is I'm going to do 0.04 times 20. And it's 0.8. I'm going to do E to that power. So I'm going to hit the E. And that gives me what E to the 0.8 is. And now I times that by 1,200. You might find another graphing calculator that will do it a different way, but if you can't get the right answer, you might have to plug it in what's in the exponent first, and then hit E to the X, and then multiply by 1,200. Okay. All right, so let's look at this next one. A bacteria has a half-life. Okay, so we have to kind of think about what does it mean when it says a half-life? Well, a half-life means that it's half as big. So that means that K is 50% because it's half of it. And when it has a half-life, that means it's getting smaller. So it's a decay. So, and that happens every 1 week. So instead of talking about years now, we're talking about weeks. So I have 25,000 bacteria, and it's continuous. Whenever they talk about half-life, it's continuous. So it's going to be E to the negative 0.50 times how long, and this is wanting 6 weeks. Okay, so we'll try with the graphing calculator first to show you those that have that. So 25,000, yep, that's right, times E to the negative 0.05 times 6. And after 6 weeks, oh, do you see what I did wrong? I made the mistake. It should have been, I'm going to enter that again. It should have been 0.5, not 0.5. Because I knew if it has a half-life, it should definitely be less than 12,000. Oops. Geez. 0.50. Now let's hit. That makes more sense because every week it gets half and then half and then half and then half. And so after 6 weeks, we have 1,244 and 68. Okay, so to use this scientific calculator, remember we have to find what the exponent is first. So 0.5, and then I do the negative, times 6 is -3, which I knew that. I don't want to get in the practice of it. Now I hit e to the x, and now I times that by 25,000. And so that's how you get your answer. Okay. I think your phones, if you turn them sideways, will have e to the x, and it might allow you to type it in more like what the graphing calculator does. But you need to try it and play around with it until you get this answer to make sure you understand the process. Okay, so growth still goes away and it grows. And instead of having a parentheses, you have to have E with the K, and K is the percent growth. For decay, it still goes towards the x-axis. And again, you have to have an E, and because it's decaying, it's a negative exponent.